Hello and welcome to Honors Function. In this last lecture on complex number, we will be looking at the geometry behind complex numbers. Let's begin. So a complex number is an element of the form a plus ib, where a and b are both real. And this is a complex number. It lives in C. To look at the geometry behind complex number, we need to be looking at the set C. Okay, so just as a real number lives in the set R, and the set R is just a numbered line, okay, a line where every point on the line corresponds to a real number and every real number corresponds to a point on the line. So this is a very simple set, okay? This is a very simple set. We need to be looking at the set of complex number. The set has a name. You can call it the set of complex number, or you can also call it the Argand plane. So the fact that it's called the Argand plane is already giving you some idea that it's a plane, okay? But it's not the customary plane that I'm used to, the Cartesian plane. Cartesian plane is two real lines that intersect at a right angle. This is a real line and this is a real line. The arrows indicate the direction, the positive direction on the line. If I move this way, I'm moving in the positive direction. If I move this way, I'm moving in the negative direction. The Argand plane looks like it's an intersection of two lines, and I guess it is the intersection of two lines, but do not confuse it with the Cartesian plane. There's only one real line, and it's this axis right here. This is a real axis. This is a real axis. And so we know what to find on the real axis: 1, 2, -1, and actually all the real numbers, okay, including all the irrational. But this right here is not a real line. This is an imaginary axis. Imaginary axis, okay? And what do you find on the imaginary axis? You find I, you find 2i, you find -i, -2i, okay? So the first thing I notice is I do not draw an arrow on my imaginary axis. Why don't I draw an arrow on my imaginary axis? Because there is no positive direction, because there is no positive numbers, right? If I give you two complex numbers, z1 and z2, you cannot say that z1 is greater than z2 or z2 is greater than z1. I can say if they're equal to each other. That's easy, right? But I cannot say if one is above the other, all right? We do not have the concept of positive complex number, right? So if there's no positive complex number, how can you move in the positive direction? That doesn't make any sense. So how do you graph a complex number? Z equals a plus ib. How do you graph that? Well, a, you go fetch a on the real line, so suppose a is right here, and ib, you go fetch it on the imaginary line. IB is going to be right here, and then it really looks like the Cartesian plane somewhat, right? And then here's the point: z equals a plus ib. So here is z equals a plus ib right here, this complex number right there. All right, that's it. This is the complex plane. The first piece of geometric result is kind of interesting right here. If here is the number z plus ib right there, okay, z plus ib right here, where is its conjugate? So I'm going to erase that, and here's the geometry behind it. Its conjugate is going to be z minus ib, and so you need to go fetch -ib on the imaginary axis, and z minus ib is right here, and that's z bar, okay, z a minus ib. Sorry, I meant a minus ib, not z minus ib. A minus ib, okay. Therefore, a complex number and its conjugate are symmetrical with respect to the real axis, okay. That's a first interesting geometrical aspect of a complex number. Let's look through the first example to another geometrical aspect of complex number. Let's go over the first example. So here's the Argand plane, and I want to plot these complex number right here. All right, let's start. Well, I know where 1 is, okay? 1 is right here. So I get this one. That's 1. And I know where I is. It's right here. I got I. Where's I squared? Well, I squared is -1. So here is I squared right here, okay? I cubed is I squared times I. I squared is -1, so it's -1 times I, and this is just -I. So I cubed is right here, I cubed. Where's I4? I4 is I2 times I2, which is -1 times -1, and this is just 1. So here is I4, same as 1. Then I5 is I4 times I, so it is 1 times I, which is just I. So this is also I5. I6, and I think you get the gist of it now, I times I5. I5 is I, so it's I times I, so it's -1. Here is I6, and we could go on like that, but basically that's going to be I7, and this is going to be I8, I9, I10. You see what I mean? It just goes on the circle right here. We say an element like that is called a cyclic element. Okay, when you increase the power, you'll go back to where you started. It's a cyclic element of ordered 4 because the only elements in these set right here are I0, I1, I2, and I3. These are the only elements in that cycle. I0 is 1, I1 is I, I2 is -1, I3 is -I. That's it. And after, when you increase the power, you'll fall back on one of these 4 elements. So, how do I find I to the 89? Well, I need to divide 89 by 4 because it's a cyclic element of ordered 4. I is a cyclic element of ordered 4. If I divide 89 by 4, I will be able to answer the question. Let's see. So let's do the Euclidean division of 89 by 4. 89 is, if you divide by 4, you find how many, what's your quotient? It's 4 times 22, which is 88, plus 1, and that's the remainder, right? You remember this old division. Dividend equals divisor times quotient plus remainder. We'll revisit that soon. So I to the 89 is just I to the 4 times 22 plus 1. Why did I write it like that? Because this is I to the 4 times 22 times I to the 1, right? Same base, you add the exponent. What is I to the 4 times 22? Another laws of exponent. It's I to the 4 to the 22 times I to the first. Okay? And what is this? I to the 4 is 1. 1 to the 22 times I to the first, and so it's just I. So you see, when you divide, when you do the division of 89 by 4, you are just interested in the remainder, because an I to the 4 will always be 1. So here you're going to have 1 to the power of the quotient, and that's just 1, no matter what, okay? So what I'm interested really is the remainder. So I can take any I. I could take I, so I'm going to let you do the last one right here, I to the 367. But look, I'm going to take I to the 13,017. Here we go. Ooh, this is difficult. No, it's not. You just eliminate all the multiples of 4. Is 1,000 a multiple of 4? Yep. Therefore, this right here is equal to I to the 317, okay? I just get rid of 1,000 because it's a multiple of 4. Is 300 a multiple of 4? Yep. So this is just I to the 17. And what's the largest multiple of 4 and 17? 16, so it's just I to the first power, which is I. You see, it's really, really simple. I'll do another one. I to the 7,893. Here we go. Oh, big one. I'm going to get rid right away of 7,800 because this is a multiple of 4, so I'm left with I to the 83. I'm going to get rid of 80. That's a multiple of 4. I'm left to I to the 13th. And what's the largest multiple of 4 in there? Oh, here we go. I don't know why. It's really per chance, but it's always 1, okay? It can be the remainders of, if you divide anything by 4, this remainder has to be smaller than the divisor, right? So this can be 0, 1, 2, or 3. These are the only 2 possibilities, all right? Please, I'm going to let you do this one. Very, very simple. Okay, let's move on to the next application of the Argand plane. So in this example, I will want to add complex number. Okay, so first let's fetch them. 2 minus 3i, so 2 and minus 3i is right here. Here we go. Here is z1. And then we have 5 plus 4i, 5, and 4i is right here. And this is z2 right here. Okay, so now I need to go fetch z1 plus z2. So z1 plus z2 is, at the real part, that's 7. At the imaginary part, and it's I. 7 plus I. Let's plot this complex number, 7 plus I. That's I, and this is 7 right here. Then, the question is, what do you notice about the figure formed by the complex numbers 0? Okay, so let me write that this is z1 plus z2 right here. Okay, so what do we notice about the figure formed by 0, this complex number, z1, z2, and z1 plus z2? Well, I don't know. Let me take a look at it. Let me connect the point. Like that, like that. Here we go. Oh, this is a parallelogram, right? It looks like it's a parallelogram. So adding complex number has a strong geometric connection. It creates a parallelogram. How can we prove it's a parallelogram? Well, you know, in a parallelogram, opposite sides are parallel, or which is the same, opposite sides are congruent, right? And so we need to measure the length of these two sides. Therefore, we need to define what's the distance between two complex numbers. Let's go to the next definition. So here is the Argand plane, and I took a complex number on it, z equals a plus ib. You remember from the first video on complex number, if you multiply a complex number with its conjugate, you will find a squared plus b squared, right? Now, a squared plus b squared, in the plane right here, what is this? Like, if this were, it's not, okay? But if it were the Cartesian plane, a squared plus b squared, you would be looking at the square of this length right here, right? By the Pythagorean theorem, like this would be, for example, this complex number would be ab instead, right? If you're in the Cartesian plane, it's ab. So that's b, that's a, and that would be a squared, square root of a squared plus b squared by the Pythagorean theorem, right? And that's just the distance between 0 and this point right here. But we are not in the Cartesian plane, right? This is not b. But still, when you take the product of a complex number by its conjugate, you find a squared plus b squared. We're going to give a name to this quantity. It's going to be called the modulus of a complex number. Okay, so this, it's sometimes read the absolute value, but actually it should be read the modulus. You will also find the magnitude. That's another word that describes it, magnitude. And some people will call it the absolute value too, and that's all right, okay? I will refer to it as the modulus of a complex number, and by definition, it's going to be the square root of a complex number times its conjugate, square root of a squared plus b squared. Therefore, the modulus of a complex number has a very interesting geometrical interpretation. It represents the distance between 0 and the complex number. This is the origin of the Argand plane, okay? So, with that in mind, we also now define the distance between two complex number, and that's super easy. If you take a complex number right here, z1, and a complex number right there, how will you define the distance between two complex number? You will say this is a modulus of z2 minus z1, right? Why? Because if you do this, you're going to find the old distance formula from the plane. This would be a2 minus a1 squared plus b2 minus b1 squared. Why? Because z2 minus z1 is a2 minus a1 plus I times b2 minus b1. Therefore, if you take the modulus of it, it's the real part. See, the modulus of a complex number is the real part square plus the imaginary part square. So it's this squared plus that square, and that's the old distance formula. That's it for the modulus. So let's go over example number 3, and you will do example number 4. I want the modulus of 1 over root 2 plus I times 1 over root 2. Well, I don't know if you remember, that's a square root of I right here. So I want the modulus of that. Well, that's super easy. It's a square root of 1 over root 2 squared plus 1 over root 2 squared. Do not put any I in it, right? The modulus of a complex number is square root of a squared plus b squared. This is a real part. This is the imaginary part. So this is square root of 1/2 plus 1/2, and that is just 1. All right. That means that this complex number lives at the distance of 1 from the origin of the plane. So it's on that circle right here. This is I, this is negative I, this is negative 1 right here. Okay. And somewhere on that circle, actually I can tell you exactly where, the A is the same as the B, right? So it's going to be on the line y equals x right here. The A is the same as the B right here. And here's a complex number right here. This is 1 over root 2 plus I over root 2. Okay? Same x right here. I shouldn't say x, but hey, it's really a strong flavor of the Cartesian plane here. And same y right there. All right. You do example number 2, and I will do example number 5. Example number 5, find the distance between these two complex numbers. So this is very easy. It's the modulus of z2 minus z1, which, by the way, I didn't tell you, but that's the same as the modulus of z1 minus z2, okay? It doesn't make a difference which one is first. So it is a square root of, what's a real part of z2 minus z1? 8 minus 5, 3. 3 squared. What's the imaginary part? Negative 3 minus, careful right here, okay, negative 3 minus 1, negative 4, so plus negative 4 squared. Oh, that's a 3, 4, 5 triangle. That's 5. So now you turn with example number 6, please. Let's finish this last lecture on complex number with the model, with the problem we took on the first introductory lecture on complex number. This kind of problems, and you will understand now why they are so easy with complex number. But before we do that, we need to notice something. It's very easy. I'll let you prove it. If you take the modulus of a product, if you take the modulus of z1 times z2, it is going to be equal to the modulus of z1 times the modulus of z2. Okay, to show that, you would need to take two complex numbers, a1 plus ib1 and a2 plus ib2, and then in this case you need to multiply them together. So if you multiply them together, you'll find something, okay, and you will have to show that this thing right there plus the real part square is going to be equal to that thing right here, which is what? The modulus of z1 is square root of a1 squared plus b1 squared times square root of a2 squared plus b2 squared. Okay, so after you're done multiplying them, put the real part right here, put the imaginary part right there, and just notice that you have the equality. So this is a very trivial property. It just takes a little bit to notice that, but it's really simple. Okay, let's apply it to this kind of problem. So what you need to do right here to express this is very simple. I recognize right here the modulus of a complex number squared, right? A squared plus b squared, that's a modulus of a complex number squared. So here's a one modulus squared, here's another modulus squared right here, and so it's a product of two modulus squared. But this is the same as the product of the two modulus, and then I'll take the square outside. I'm allowed to do that, right? Take the square outside. But now the product of the two modulus is the modulus of the product, z1 times z2. And that's it. And I'll take the square of that. And I'm done. That's it. It's finished. With that, we can find the two numbers. So it seems really trivial when you look at this, but look at the really nice application. Let me show you. So I'm going to say that z1 is 3 plus 5i, right? And z2 is 2 plus 3i. It doesn't matter. You could also say it's like, it doesn't matter which one is I, okay? You could also say it's 5 plus 3i. It really doesn't matter. Anyway, let's do it like that. So, in this case, 3 squared, what is z1? What is the modulus of z1 squared? It's 3 squared plus 5 squared, right? And the modulus of z2 squared is 2 squared plus 3 squared, right? So here on this side, you have the product of the squares of the modulus. On the right side, I know the product of the square of the modulus is supposed to be this. So how about I figure out what z1 times z2 is? z1 times z2 is what? 3 plus 5i times 2 plus 3i. Okay, let's expand. Where's your real part? 2 times 3 is 6. 5i times 3i. That's 15i squared, negative 15. Here's my real part, negative 15. Let's fetch my imaginary part. Imaginary part, 3 times 3, 9. 5 times 2, 10. Done. I have my two numbers, right? This is negative 9 plus 19i. Okay? And this is, what is this? This is z1 times z2. z1 times z2. And so what is now? What is the modulus of z1 times z2 squared? This is negative 9 squared plus 19 squared. And so I got my two number. This is the same as 9 squared, forget about the negative, right? Plus 19 squared. Super easy and super quick. Please do the last one. Thank you for watching.